Welcome. The topics for today are convergence of empirical cumulative distribution functions and bootstrapping. So let's get started. The Glivenko-Cantelli theorem says that the empirical cumulative distribution function, estimated from n observations drawn from the same distribution, approaches the actual cumulative distribution function as the number of observations goes to infinity, even when we evaluate the difference at the worst point x. So the biggest difference between the empirical CDF f hat and the actual CDF f, it converges to 0 as the number of observations goes to infinity. We'll want to visualize that to make sense of it. So in problem 1, we're going to generate some observations and plot a cumulative distribution function. So we'll do it for a range of values from 100 up to 100,000. We'll compute the empirical CDF as well as the actual CDF for this distribution that we're drawing observations from, and we'll compare them. And remember that the empirical CDF picks up the probability masses for the observations as you move from left to right. So if we've sorted the observations, let's say n is 4 here, and we move from left to right, picking them up one at a time, then we end up with a step plot where the jumps happen at the locations of the observations, and the y values for each jump are just 1 over n. So the first y value is 1 over 4, and then the second y value is 2 over 4, and so on until we get to 1. So what we need to do is make a step plot whose x values are the sorted observations and whose y values are 1 over n, 2 over n, and so on up to n over n. And we can write this in Julia as 1 colon n divided by n. So just the numbers 1 to n and then divide the whole thing by n. In math notation, we can write the empirical CDF as 1 over n times the sum of the indicator of big Xi less than x. So this blackboard bold 1 means the function that is 1 when the condition is satisfied and 0 otherwise. So in other words, this sum is counting 1 for every observation that's less than x and 0 for all the rest of them. So in total, it's counting the number of observations less than the value x, and then we're dividing by n. So ultimately, it's counting the proportion of observations left of each value x. And the CDF for the normal distribution looks like this, and we can just call that from the distributions package without having to write this formula out. So we begin by generating some sizes for our samples ranging from 10 squared to 10 to the 5th, and we come up with 100 of them. And we actually make the samples by calling the rand function. So we supply the distribution that we want the random variables to come from, and then we supply how many of them we want. So we do that for each number of samples in this sample size list. And then we sort them because, as we said earlier, when we make this step plot, we'll want to have the x values sorted. So as we said before, we're going to make a plot where our x values are the observations, and they've already been sorted, so we don't need to sort them here. And the y values are 1 over n, 2 over n, and so on up to 1. And the type of plot we want is called a step plot. And we need to say step pre here because when you make a step plot, you have to choose for each x comma y pair whether the step should proceed to the right and then go up at the next one, or go up and then move to the right when it gets to the next y value. And you can try it both ways and see which one is right, step pre and step post, and it happens to be step pre here. So we'll call that our CDF. I want to put the legend in the top left because the CDF is going to move from the bottom left to the top right. So we have the empirical CDF in blue and the actual in red, and they're very close. If we go all the way out to the end of the list, so there are 100,000 observations in this sample, then it's barely distinguishable on the plot. At the beginning, it's going to be quite different. So if there are only 100 observations, the deviations are noticeable, and you can see the step plot more clearly. Philosophically, what this is telling us is that if we get many observations from a distribution, we can see the distribution in a very tangible sense by plotting its cumulative distribution function. And that, with high probability, is going to be very close to the actual CDF. So any stuff we want to do with the distribution that involves the CDF, it's probably going to be fine to just use the empirical CDF instead. So in problem 2, we raise the challenge level a little bit by giving ourselves this cumulative distribution function to try to sample from. So this distribution function is spreading mass out between -2 and -1 because all of these values are possibilities. But otherwise, the only possible values are where these jumps are. So -1, 0, and 2. So those are the only places where you pick up probability mass. Everywhere else, as you move from left to right, it's flat. So that's telling you there's no probability mass here. Like between -1 and 0, it's totally flat, which means there's no mass in that interval. So the main idea we need to sample from this cumulative distribution function is the CDF trick. The way it works is we sample a uniform random variable between 0 and 1, which we visualize on the graph here as being along the y-axis in the first unit of this segment here. And then we move left and right, whatever value we get, we move left and right until we hit the graph, and then we go down to that x value. So if we're up here at like 0.6, we would go left to hit the graph here, and then down, and we'd return -1. So if our uniform variable falls anywhere in this interval, then we're going to hit the graph here, and we're going to get -1. So you can see how the bigger the jump is, the more likely that particular x value is. So we just need to write down an inverse function for this function. So I'm going to call it f inverse with these Unicode characters. So \caret hyphen and then tab complete. That becomes a superscript minus and then a superscript 1. You could call it something else if you're uncomfortable with the Unicode characters. This is just a name. And we want to plug in some value. Let's call it u because it's going to end up being a uniform random variable between 0 and 1. You could call it whatever you want. So we just need to think about the different pieces that have to be considered here. So the first one is from 0 up to half. Anywhere along that stretch where we hit is going to just depend on this diagonal line. So if u is less than a half, then we need to invert this function. So we can just write down a slope and intercept formula and invert it. And when we do that, we're going to get 2u minus 2. And we can just double check that that's right. If we plug in 0, we should get -2, and we actually get -2, so that checks out. And we plug in a half, we should get -1, and that checks out. So this is the right formula. So otherwise, if u is less than 3/4, then we're going to hit -1, so we should return that value. If u is less than 7/8, but bigger than 3/4, then we're going to get 0. And if all of those conditions fail, then we're bigger than 7/8, so we're in this top little bit here, and we have to move to the right to hit the graph, and then we pick it up at 2, so we should return the value 2. So that's our function f inverse, and we can plot its empirical CDF just like we did above. So if we run this a few times, what we see is that the empirical CDF does stay very close to the cumulative distribution function, even for 1,000 observations here. So this is giving us some confidence that we're doing the right thing. We're successfully sampling from this distribution, and we can see that the graph of the empirical CDF hugs the graph of the actual CDF. We can do a little bit better than the Glivenko-Cantelli theorem by supplying some bounds. So instead of just saying, oh, it's close and it gets closer as n goes to infinity, we can say specifically for a particular value of n, what sort of band do you need to put around the empirical CDF to make sure with high probability that you trap the actual CDF, or vice versa. How much up and down do you need to go from the true CDF in order to make sure to trap the empirical CDF? So the theorem that gives us that result is called the DKW inequality. And it says that the probability that the maximum separation between the empirical CDF and the actual CDF is no more than epsilon. So in other words, the probability if we put an epsilon band around one of these functions that it will trap the other one is at least 1 minus 2e to the minus 2n epsilon squared. So if n goes to infinity in this expression, then you're going to get e to the minus a large negative number. That's going to be really close to 0. And so your probability of success is going to be very close to 1, but greater than 1 minus some small value. We can rearrange this inequality a bit to get the expression on the right-hand side to be any particular value we want. Let's call it 1 minus alpha. So alpha is going to be this expression that's being subtracted from 1. So if we solve that equation for epsilon in terms of alpha and n, we find that this is the bandwidth that we need to be trapping the empirical CDF in a band around the actual CDF with probability at least 1 minus alpha. So once again, we're just going to draw some of these things and kind of see how it works out. So the first thing we're going to do is find epsilon in terms of n and alpha. So we look at this function that maps epsilon to this expression for alpha minus 0.5, and we look for a 0 of that. In other words, we're looking to solve this equation. So here we're considering an alpha value of 0.05, which is expressed here with this 95% value that we're supposed to be using for this confidence band. And we have to choose a place to start and we're expecting to find generally small epsilon values, so we just start 0.1. This is an easy function to invert, so it doesn't matter that much where you start. Okay, and so we have this value of epsilon, and now let's just plot an empirical CDF and an actual CDF, and plot an epsilon envelope around one of them and see that the other one falls inside of it. So we plot our observations. So we get this graph. Now I need to move up and down to plot a window around this graph. So we add epsilon to each of these y values to make the graph just scoot up by epsilon units. And to add values to an array in Julia, you need to do point plus to tell it you're adding this epsilon value to each element in this array. And we also want to supply a bottom of the envelope so it can fill between. And the way you do that in the plots package is you supply a keyword argument called fill range. So that's going to be scooted down epsilon. It's going to be hard to see other elements of the plot unless we make it translucent a bit. So let's set the opacity to 0.5. And we don't want to see the line, we just want to see the band. So we'll set the line width to 0. So that's our band around the empirical CDF, and we'll want to plot the actual CDF to check that it falls within that orange window. All right, so here we go. We see that the true CDF falls in this band, but the band is maybe not being super wasteful because you can see it gets quite close to jumping outside this band here. So we can change the number of observations and we should get a tighter band, and it should still fall inside that band with 95% probability or more. We can try again. If we do this a few times, eventually we'll see it. You see here it gets quite close to jumping outside at this point. So on average, you have to try it 20 times in order to see the true CDF fall outside this band. It gets pretty close there too. Really close there. It's almost touching right around this point. Okay, finally. The green curve jumps outside the orange band here. So this confidence band has some probability of failing, and here it does. So with n equals 10,000, you can see the band is even tighter, and with an n more like 100, it's going to be a much wider band. So now let's move on to our second topic, which is bootstrapping. So let's suppose you have a distribution nu, which I'm not showing in this picture. Instead, what we get are 7 observations drawn from that distribution, and we can associate those 7 observations with the empirical measure nu hat, which assigns probability mass 1/7 at each of those 7 locations. And suppose that t is a statistical functional, like let's say the median of nu, in other words, f inverse of 1/2, where f is the cumulative distribution function of nu. So again, we don't know the actual distribution nu, we only know this approximation nu hat. So what we could do instead is approximate t of nu with t of nu hat and compute the median of this empirical measure, which is this value. Notice that this is a random variable. We're drawing 7 observations from this distribution nu, and we put them in order and select the middle one. And if we selected 7 fresh observations, we would potentially get a different median and so on. So this is a random variable. It depends on the observations that we actually saw. And you might want to put a confidence interval around this random variable and say how much do we expect it to be fluctuating on average. So that gives rise to a new statistical functional, which we'll call T2. So this statistical functional gives us the standard error of this estimator. But ultimately, it is a statistical functional because it's defined purely in terms of the original distribution nu. We have the distribution nu, we sample 7 independent observations from it and find the median. That's a random variable. We can ask for its standard deviation, and that gives us a number. So we go from a measure nu to a number. So this is a statistical functional. We're not going to be able to feasibly evaluate it exactly, even if we want to just approximate it with its own plug-in estimator. So again, we don't know nu in this case. So what we want to do is find the plug-in estimator of this statistical functional. But even then, we're not going to be able to evaluate it exactly. If you think about how you would go about that, you're going to end up with a very large sample space, and the computation is going to get quite messy. And that's just with 7 independent observations. Typically, in an application, you would have many more, and it gets really out of hand. So the idea is to just use Monte Carlo. So that's what bootstrapping is in a nutshell, approximating the plug-in estimator of a statistical functional through Monte Carlo. So following that idea, we'll draw 7 observations from the empirical distribution, which amounts to the same thing as just drawing 7 observations uniformly and independently from those 7 observations that we have. So we're not going to take all 7 of them necessarily because we're drawing with replacement. So an independent draw from a discrete distribution has a positive probability of producing the same value twice. So when we draw 7 observations from the empirical distribution, we won't be just reproducing the same data over and over again. So we repeat that procedure b times, where b is typically some large number, and then we find the standard deviation of the resulting list. So this last part is the Monte Carlo step. So let's look at some different examples. So suppose we have these data which came from an exponential distribution with some parameter lambda. And the parameter for an exponential distribution is 1 over the mean. So to try to extract this parameter lambda, we're going to define the statistical functional which computes 1 over the mean of a distribution. So the plug-in estimator of t is easy to evaluate since we just need to compute the expectation of this empirical measure and then reciprocate it. So that's just 1 over the mean of the data. So our estimate for lambda is 0.046. But this exact number doesn't tell us very much because we don't know how close to expect it to be to the actual parameter lambda. So we want to know the standard error of this estimator so we can put some confidence interval around it. And notice that the standard error of this estimator is itself a statistical functional. So it's the point we were making earlier. It's defined to be the standard deviation of 8 independent observations from the underlying distribution nu. So we only get these observations, we don't get nu, but we can still form the plug-in estimator of this new statistical functional, the standard error of the first estimator. And we can do that through simulation. So let's use bootstrapping to estimate the standard error of this plug-in estimator. We're going to compute 1 over the mean for several samples obtained by drawing from the sample that we have. So we can do that with the sample function. So we sample from data, and the number of samples we take is equal to the amount of data that we have. So the fact that these two values are the same is coming from the fact that the number of observations that we see shows up in the second statistical functional. So the statistical functional whose value we're trying to estimate here is the standard error of 8 independent draws from this distribution. And the reason we choose 8 is because that is the number that goes into our first statistical functional, which computes 1 over the mean. So anyway, here are our bootstrap estimates. And notice they're different from each other. So again, we're sampling with replacement here. So we're getting some different observations. So this is just the plug-in estimator for this second statistical functional. So we can ask whatever question we want about this distribution based on the very large number of observations that we can generate from it. In particular, we can ask for the standard deviation, and we find that it's about 0.0169. So assuming the normal approximation, we should move up and down a couple of these units away from this center value in order to trap 95% of the probability mass for this estimator. However, we don't have to rely on the normal approximation. While we're bootstrapping, we have a very detailed picture of the distribution of this estimator, at least with respect to the empirical distribution. In other words, the quantiles are quantities that we can estimate directly from our bootstrap estimates. And we can use those to make a confidence interval instead. So we just use the quantile function. Where's the right place to draw the threshold to have exactly 5% of the bootstrap estimates below and 95% above? So we can compute these values at the same time with this quantile function. So this is going to return the 5% quantile where we have 5% of these estimates to the left and 95% to the right, as well as the 95% interval where you have 95% to the left and only 5 to the right. And this gives us some more sensible results. So 0.029 is our left edge of our confidence interval, and 0.083 is the right edge of our bootstrap confidence interval. So it's crucial to point out here, this is not going to be totally reliable because we're estimating t of new hat, not t of new. In some situations, t of new hat and t of new might not be close to one another. So to underscore that point a little bit, let's do this example where we have a hold on what's going on. We're going to draw 20 independent random variables, x1 up to x20, from the uniform distribution on 0, 1. And here we can compute the exact standard error of the sample mean based on our knowledge of the distribution of these random variables. And then we can compute the bootstrap estimator and compare the two. So we get our 20 observations from the uniform distribution on 0, 1. Here they are. And we want to know, if we compute the sample mean here, what's the standard error of the sample mean? So ultimately, the statistical function we're interested in is not the mean of the distribution, it's the standard error of the sample mean when you draw 20 times from the distribution. So that's a significantly more complex functional, and we're only going to be able to evaluate it exactly here because we know the distribution that these random variables are coming from, and because we understand how variance and linear combinations interact. So the constant comes out and becomes 1 over 20 squared. And the variance distributes across the plus sign because these random variables are independent. So we end up with 20 copies of the variance of x1 divided by 20 squared. And the variance of a uniform random variable is the length of the interval squared divided by 12. So in this case, that's 1/12. So it comes out to 1 over 240. That's the variance of the sample mean for 20 independent observations from the unit interval 0, 1. The actual standard error is the square root of 1 over 240, which is about 0.0645. And to bootstrap, what we want to do is sample from our observations 20 times. So we're treating the empirical distribution like it's the actual measure, and we're sampling from it 20 times because that's what our statistical functional says to do. And we compute our estimator for the result. So that's just going to be the mean. So we do that a bunch of times, and we compute the standard deviation of the result. And what we find is that we're kind of far off here. This is 0.064 and this is 0.054. And this second estimate is quite accurate. If we run it several times, it's not going to deviate very much. We can make it even more accurate by doing even more bootstrap samples, like 1 million. That's no big deal. And we can see that we're getting really, really close here. We're estimating very precisely the value of this standard error, but for the observations measure, not for the original actual measure. So we're still ultimately limited here by the fact that we only have 20 observations. They're only approximating the uniform distribution so well. And running our number of bootstrap samples up only allows us to approximate t of new hat very accurately. It does not allow us access to t of new itself. So to recap, today we studied the Glivenko-Cantelli theorem and the DKW inequality, which tell us that the empirical CDF of many independent observations drawn from a distribution closely matches the CDF of that distribution. And we also talked about bootstrapping, which is approximating a plugin estimator through simulation. And applying Monte Carlo to an empirical distribution amounts to just sampling uniformly with replacement from that distribution.